So welcome to unit 3 or 4, I guess, using energy changes and rates of reactions when we look at chemical reactions. So this whole unit is going to be centered on calculating energy and how much energy is involved in a reaction. And then later on we're going to look at rates of reaction. So we're going to look at slow versus fast reactions and what actually will affect those. So let's get started with some key terms and some basic fundamentals for this unit. So to start off, another way of referring to energy changes is by thermochemistry. So thermo meaning heat, and chemistry obviously are the reactions. So we're looking at the heat that is involved, or energy that is involved in chemical reactions. So that's our first point, the study of energy changes that accompany physical or chemical changes in matter. All of thermodynamics or thermochemistry depends on the law of conservation of energy, okay? This states that the total energy of any system and its surroundings has to remain the same. So energy it can be converted from one form to another, but it should remain the same the whole way through. The changes that can occur in matter can be classified as a physical change, a chemical change, or a nuclear change. Now, obviously, in this class, we're not going to do any examples of nuclear reactions, but we can see some physical and some chemical changes, and we're going to measure how much energy is involved in those. So here are a couple of pictures just to show you some different types of reactions. So some physical reactions of water evaporating, condensing, and all that. Some chemical changes, for example, igniting fuel for a rocket, and nuclear changes, so what happens on our sun. All right, so let's keep going with some definitions. So again, here are your physical, chemical, and nuclear changes. I think there's one more thing there. So I'll give you a second to copy this down, and then I'll explain each point really quickly. But basically, any change that we study is always accompanied by a change of energy. Sometimes the change of energy is a great change. Sometimes we don't have a very big change, but there always is energy involved in every reaction. So for example, in a physical reaction, it's a change in the form of a substance. So no chemical bonds are broken. An example is hydrogen boiling at negative 252 degrees Celsius. So what happens to go from a liquid to a gas? We have to add some energy in the form of heat. In a chemical change, the chemical bonds are broken between atoms, and new bonds are formed to create new substances. So the example here is hydrogen can be burned as a fuel in the space shuttle's engines. So in this case, when that happens, obviously energy is released in the form of heat. You could feel the heat from the burning. And then a nuclear reaction is a change in the protons or neutrons in the nucleus of an atom, and that results in a new atom. So for example, hydrogen undergoes nuclear fusion in the sun that produces helium. So there are 3 examples there. A few more key terms. We're not quite done with those yet. So these are important. Make sure you fill them in. First one, a chemical system is the substances that are undergoing the change. So usually that's the reaction. The surroundings are the system's environment. Thermal energy is energy available from a substance as a result of the motion of its molecules. Temperature is the average kinetic energy of the molecules in a sample. And heat, which is denoted Q for this course, is the amount of energy transferred between substances, and we measure it in joules, which is J. So basically, energy always flows between substances because of their differences in temperature. So we're going to look at the difference between thermal energy, temperature, and heat in a lot more detail as we go through the rest of this unit. All right, a few more key terms. You've probably seen these before. An exothermic reaction, that's when you release thermal energy. So what happens? Heat flows from the system into the surroundings, usually causing an increase in the temperature of the surroundings. When we do this, because we're losing heat, we give Q a negative value. And the opposite of that is an endothermic, which is when we absorb thermal energy. And in this case, heat flows into the system from the surroundings, and that causes a decrease in the temperature of the surroundings, and that's what we feel. So we say that Q has a positive value because we're adding it in to the system. So Here are two diagrams just to help you to understand what's going on here. So in A, this is an exothermic reaction, okay? So energy is being released to the surroundings, and the surroundings is basically what we can feel and what we can measure. So when heat is being lost to the surroundings, it's an exothermic reaction, and your Q is negative because you're losing it. And if the surroundings is if the system is going to absorb heat from the surroundings, you have an endothermic reaction. And because heat is sort of going from the surroundings into the surroundings end up feeling cooler than the system. So we give that a positive Q value. All right. How do we measure these energy changes in chemical reactions? Well, there is your new best friend for this unit called calorimetry. And this is a technique that we're going to use many, many times to measure the energy changes in chemical systems. So what we have to come to terms with is that different substances can vary in their ability to absorb amounts of heat. So that means that every substance has what's called a specific heat capacity, and that's the amount of energy that's required to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 degree Kelvin. Okay, page 301 of your textbook has a table of this to show you a bunch of different specific heat capacities for different compounds. The amount of heat transferred therefore depends on how big the sample is, the mass of the sample. So obviously if something has a larger mass, you can transfer more heat. The temperature change, oh, that should be a delta T. I don't know what my symbol is there, but right there, that should be a delta T. And that's measured in degrees Celsius or in kelvins. And then specific heat capacity, which is how much that heat can actually be absorbed from that substance. So when we put all these things together, we get a fancy new formula, which is sort of your new way to calculate energy changes for this unit. And you get this Q equals MC delta T. So again, what you've got, oh, I should change this to a delta. Sorry, if you guys can do that in your notes, that would be great. All right, so that's your new favorite formula. We're going to use it lots, and let's maybe try an example with it right off the bat. So, sample problem number 1. Many water heaters in your house use the combustion of natural gas, so we're going to assume that's methane and only methane, to heat water in the tank. If you have 150 liters of water at 10 degrees is heated to 65 degrees, how much heat will actually flow into the water? So how much sort of energy or heat is required there? All right, so the first thing I would do in a problem like this is start by writing down what's given to you in the equation or in the question. Oh dear, what just happened? There we go, sorry. Okay, and now I can write on my smartboard. Oh, that didn't look too pretty. Okay, so can we do this? There we go. So in this case, what is given to you in the question? I've given you a volume of water, which is 150 liters. Okay, we can easily convert this to mass. Okay, so eventually we're going to want to plug into this formula Q equals MC delta T to determine the amount of heat. Remember, Q is heat. Okay, so in order to do that, we need to find the mass of water, the specific heat capacity of water, and the temperature change of the water. So to find the mass of water, I'm not really given that in the question, but I am given liters, okay? So you have to remember that, sort of a side note, if you have 1 milliliter of water, it's the same as 1 gram of water. So if we can do that conversion, basically, if you want to do the conversion yourself, if you have a kilogram, sorry, 1 kilogram of water, that's the same as saying 1 liter, or 1,000 milliliters. Okay, so I basically multiplied by 1,000 to get that. So now that I know that, I can figure out my volume, or sorry, not my volume, I have my volume, I can figure out my mass of water. So my mass of water is actually going to be 150 liters times obviously 1 kilogram per liter of water. So I get 150 kilograms of water. And I just move this over here. Okay. I also have the specific heat capacity of water, which is a constant. You're always given this, but by the end of probably this week, you're probably going to have this memorized. So the specific heat capacity for water, this is water because that's a substance that's getting heated in this case, it's 4.18, and your units are joules per gram degree Celsius. Okay, and then the last thing you can do is your temperature change. So your delta T ends up being your final temperature, which is 65 degrees minus 10 degrees. Okay, so your actual change in temperature is 55 degrees Celsius. So now we can plug those three numbers into our equation. The only thing we have to remember is that I gave you a mass in kilograms and I gave you a specific heat capacity that is grams. So you have to make sure your units are consistent. So when I plug in for my mass, I'm going to just erase that. When I plug in for my mass, I'm going to want to do it in grams. So I'm going to call it 150,000 grams. That's equal to 150 kilograms. And then I times that by 4.18 joules per gram times degree Celsius. And I times that by 55 degrees Celsius. So I multiply all those numbers together, and I get 3.45 times 10 to the 7 joules. Okay, a very common unit for heat or for energy is the kilojoule, which is 1,000 joules. So this is the same as 3.45 times 10 to the 4 kilojoules. Okay, so that's 1,000 joules. So that's how you answer the question. Done. So let's try another one. If you'd like, put the video on pause and see if you can do this yourself. But I'm going to go through the whole answer with you right now. So you have 25 grams of aluminum and it cools from 310 degrees Celsius to 37 degrees Celsius. How many joules of heat energy are lost by the sample? So again, I usually start by writing down what's given to me in the question. So I'm given the mass of aluminum, and that's 25 grams. I'm giving the specific heat capacity of aluminum in your textbook. So if I look that up in your textbook, it's 0.902 joules per gram degree Celsius. And my delta T. Again, when you're doing a change in temperature, you always do your final minus your initial, so TF minus TI. So my final temperature in this case is 37. My initial temperature was 310. So my temperature difference in this case is negative 273 degrees Celsius. So again, I've got everything I need to punch into my Q equals MC delta T equation. So my mass is 25 grams. My specific heat capacity, 902 joules per gram degree Celsius. And my temperature change, negative 273 degrees Celsius. Multiply those numbers on my calculator and you should get negative 6.2 times 10 to the 3 joules, or negative 6.2 kilojoules of energy. What does that negative mean? It means we have a loss of energy, which makes sense because in order to bring the temperature down, you have to lose some energy in the form of heat somehow. Okay, one more example, and then I'm going to show you a couple more ways to represent this heat transfer and energy changes. So again, if you'd like to pause the video now, I'll go through the answer. What we're going to do is we're going to calculate the molar heat capacity, which is capital C, of water. So the molar heat capacity, it's the same thing, but instead of having grams, we've got joules per mole degree Celsius, which will help us out a lot when we're going to deal later on with actual chemical reactions, because we know by now that whenever we're doing quantities with chemical reactions, we always convert from grams to mole. So you are going to end up using the molar heat capacity a lot more often than the specific heat capacity. But what we can do is we can alternate between the two, the specific heat capacity and the molar heat capacity. So if I have what I know about water, little c is 4.18 joules per gram degree Celsius. Okay. In order to convert from grams to moles, you need the molar mass of water, which is 18.02 grams per mole. So to calculate capital C, it ends up being little c times the molar mass. So in this case, it'll be 4.18 joules per gram degree Celsius times 18.02 grams per mole. So if you look at your units, for those of you who like to use units, here I've got grams on the bottom and grams on top of a fraction, so they end up canceling out. Now what are my new units? I still have joules up top of my fraction. I still have degrees Celsius on the bottom, and now I also have moles on the bottom, which is the units that I'm looking for if you look back to the question. So if I multiply those two numbers together, my units work out, so I know I did it right. 75.3 joules per mole degree Kelvin. That's your capital C, so that's your molar heat capacity. So that's the amount of energy it will be required to raise 1 mole of water up by 1 degree. All right, last little thing before we end our first video is heat transfer and enthalpy change. So I guess let's just go through these points so you can fill in your notes. The internal energy of a system is equal to the sum of the potential and kinetic energy of all species in the system. So those of you who have taken some physics, you might recognize your conservation of energy laws here with your potential and your kinetic energy. But basically what happens is all the energy of the system is in potential or kinetic energy. So it's just a matter of how much is which. So kinetic energy is the energy of motion. So where do we see motion in chemistry? Well, we've got moving electrons in atoms, and we also have vibrating, rotating, and translating of atoms and molecules. So basically, molecules are always moving around. Potential energy is in the form of many things. So we have the nuclear potential energy of protons and neutrons. That's not really going to affect any of our calculations because, again, we're not going to split apart any nuclei. But we do have energy, potential energy, that's stored energy in the form of bonds and in the form of intra and intermolecular forces. So this is what we have to keep in mind throughout this entire unit, is that when we're looking at this change in energy of a system, we know it's not possible to measure all of these energies. It's not possible to measure how much molecules are moving around or how much energy is present in the nucleus and all that. But what we can do is we can study the energy absorbed or released to the surroundings during a change in the system. That is what we call the change in enthalpy, which is delta H. So this is a very new concept. We're going to learn a lot more about it in the coming videos. So this is just a quick introduction to it. So here's a quick graph. Where are we? There we go. So basically, anytime you have a reaction, whatever you start off with ends up being sort of your opposite of your Q. So again, I've got this weird symbol for delta. I don't know why. There we go. Oh, what just happened here? There we go. I'll grab that after. So if you start off with your reactants saying have high potential energy, so lots of bonds and lots of stored energy, and low kinetic energy, meaning they're not moving around, then by the time the reaction's done, the flip of that should happen, and you'll end up with high kinetic energy or lots of motion, and low potential energy, which means not a lot of stored energy. The difference there between the two, between the high and low potential and kinetic energy, ends up being the difference in energy, which is Q, which is what we've been calculating. It also ends up being the enthalpy change in the system. So this is an example of an exothermic change that shows that the potential energy of the system equals the change in kinetic energy of the surroundings. So I'm not going to go through too much more detail about this diagram. We will come back to it later on in some other videos. So for now, as long as you can understand your Q equals MC delta T equation, you should be good for this part of the video. And we're going to keep looking at these changes in kinetic and potential energy in some other videos coming up. So hopefully you're good with all of that, and we are done for this video. See you in class.